Okay, good morning and happy Friday on this sunny mid-Michigan morning. Just a couple reminders. Participation 5 opened this morning, so you've got until Sunday at 11:59 to complete that. The softening homework is due on Wednesday, and along with that, you will also submit tutorial 1 assignment, which is a conceptual drawing of a flocculation basin. Office hours, again, will be Monday, Wednesday, 4 to 5 p.m. I will put the Zoom link again in my weekly email, and it'll remain from the same from last week. So I'd like to start the unit on sedimentation today. We'll talk about sedimentation theory. We'll talk about the different types of sedimentation. We'll then go into sedimentation practice and then design. So this will take about 4 lectures, but we'll move through the unit. So what I'd like to do is just a recap of where we are in terms of the water treatment process. So let's look at surface water first. So if we have a body of water, we extract that water. What is the first process we would use? How do we first treat that water?
Some sort of filtration, right? Like to get out the big stuff.
The big stuff. So we're going to remove it with some sort of screening. Typically a bar screen, which is basically, think of it as a really large sieve with typically about 1-inch slots in it. We may then have a finer screen, but it's some sort of screening, exactly, to remove the big stuff, to remove the twigs, to keep the fish out of the pump and pipes. We may also treat with some chemicals to either prevent zebra mussels from attaching to the piping system. We may also pre-disinfect, but screening is essentially always done. From there, the water flows into what next unit up. So the next thing we would typically want to do.
You do coagulate the sediments.
Is coagulation. So the first thing we'll do is some sort of rapid mix. So we'll add our coagulant. From there, the water flows into
flocculation basin.
Exactly. I'll draw it as a paddle wheel flocculator. And after flocculation, we have
That should be the sedimentation next, right?
Okay. And we won't talk about the rest of it. We'll add that as we go. Okay. So that's surface water treatment. If we have groundwater treatment, so if we're looking at groundwater, we have a pump. Typically, we have a well screen. If we have softening, and we'll write this as softening, what's the first process? So we have some sort of screening in the wells. What's the first thing we're going to do?
We need to remove some CO2.
Okay, so exactly. If we have high CO2, we may have, and it's aeration, to remove CO2 and oxidize iron and manganese. Okay. So we may or may not have that. It really depends on the level of CO2. But if your CO2 levels are high, if iron and manganese is a problem, then you'll have aeration first to remove the CO2 and to oxidize the iron and manganese. What next? What are we adding?
Lime and soda ash.
Exactly. So we, again, We have a rapid mix. And I'm just going to write this as one process, even though we talked about multiple stages. Okay, so we have lime soda ash. From there we go into a flocculation basin. Really, this is a reaction basin, but we often refer to it as a flocculation basin. And from there, we then, water flows where? Into sedimentation. The goal is by the end of the semester, all of you can draw these drawings without too much thought, and you really understand how all the pieces fit together. Okay, so we produce it, we have sedimentation. This is where we're going to produce the calcium carbonate and the magnesium hydroxide sludge, and then the effluent would move into a filtration system, and we'll talk about filtration next. So when we're talking about sedimentation, the water's then flowing into these typically larger basins, often operated as a plug flow or nearly plug flow system. And the goal is that the water is almost devoid of turbulence. So we want to allow the flocks or the precipitated sludge, calcium carbonate or magnesium hydroxide, to collect and settle at the bottom. And then the flock may flow into a hopper and then be mechanically or pumped, physically removed from the system. I've got a couple of YouTube videos. We'll actually look at those later on in the semester, in the unit. So there's a number of types of sedimentation that we will talk about. They really have to do with how the particles interact with one another. So type 1 is what we refer to as settling as discrete particles. So these particles are not interacting with one another, so there's no flocculation during sedimentation. So if you can kind of think about if you mix sand and water and you allow that sand to settle, the sand just settles and it's not interacting with another particle. There's no particle growth during sedimentation. So this can occur if you have pre-sedimentation for sand removal in a surface water treatment. I didn't draw that, but you could have pre-sedimentation before you even do the rapid mixing. In a filter bed, we'll talk much more about this, but we'll talk about backwashing. So basically, you pump water up through the filter, you fluidize the bed, that releases the particles, and then you allow the sand to settle again. So as the sand particles settle, they're settling by type 1 sedimentation. They're settling as discrete particles. In wastewater treatment, we typically will have what we refer to as a grit chamber. So we're removing predominantly inorganic material, kind of the size of coffee grinds. It's silt, coffee grinds, eggshells, particles that get put down the drain. And these need to be removed before subsequent treatment to protect your pumps. And then in a quiet stream, sand particles will settle by type 1 sedimentation. So what we will do is we'll look at this discrete settling. So we have a drag force, we have buoyancy forces, and we have gravitational forces acting on these particles as they settle in this basin. So we'll as we look at this, we'll look at particles. We'll assume that they have a density of rho p for particle, a spherical volume of V, a mass m, and a cross-sectional area, and I'll actually add the p there. So we'll need to look at the coefficient of drag, and we'll also need to consider the density of the water. Okay. So we'll go through these equations, and basically when a particle reaches terminal settling velocity, that is, the acceleration is zero, the various forces are balanced. So we have a balance between the force of gravity, okay, which is acting down, and the buoyancy and the drag force. So when we have zero acceleration, as I mentioned, then what we have is the terminal settling velocity. It's the maximum settling velocity. If we have a spherical particle, and we will assume spherical particles, and that spherical particle has a diameter, we can write the terminal settling velocity in this form here. Now, what we typically want is a laminar flow regime. Okay? So if we have laminar flow, we can use the Reynolds number here to describe the flow regime. So if we have laminar flow, the coefficient of drag can be approximated as 24 divided by the Reynolds number if we have a spherical particle. And as I mentioned, we're only going to look at spherical particles. For the transition region between laminar flow and turbulent flow, the coefficient of drag is a more complicated equation shown here. And it's a function, again, of Reynolds number. Now, Reynolds number is, to kind of review a little bit of fluids, it's defined as the ratio of the momentum forces to the viscous forces. And it consequently defines the relative importance of these two types of forces for given flow conditions. So for spherical particles and laminar flow, so we have here spherical particles and laminar flow, the terminal settling velocity is a function of gravitational acceleration, the difference in the density of your particle in water, the diameter of the particle squared, and the dynamic viscosity of the water. What we have is Stokes' law. If the flow regime is unknown, then we need to use the more accurate equation, which I gave previously. If you're in the transitional flow regime, so you're typically between a Reynolds number of, and I should have changed this to capital R. I tried to change it to the textbook notation. If you're in the transitional flow regime, so Reynolds number is between 2 and 500, then coefficient of drag is approximately equal to 18.5 divided by the Reynolds number to the 0.6 power, and we have this more complicated equation right here. So we have multiple equations that we can use for the settling velocity. For the most part, you will attempt to operate in a laminar flow, so the simpler equation should work. Okay. So let's look at an example here. So what we have is a rapid sand filter, and that's backwashed. So you can think of your sand filter as basically a box. And that box is filled with a gravel support, shown in yellow. And on top of that, a sand. Now, during backwashing, what we do is we pump water upwards. Normally, water is flowing down through the filter. We pump water upwards, causing the sand bed to expand. The level of water rises above that gravel support so that we'd have a level of water much higher. So the situation we have is we backwash this filter. We have a sand particle of diameter 0.1 millimeters with a density of 2,644 kilograms per meter cubed. And it is 1.0 meters above the sand bed. And you're asked, how long does it take for the particles to settle, for these particles that are 1 meter above, how long does it take for that particle to settle 1 meter to hit the gravel support? So we've got a particle up here during backwashing, and then we're looking at how long it takes to settle. Okay. How far back should I go? I'm sorry, I didn't notice the chat.
I was wondering about when you said the flow regime is unknown.
If the flow regime is unknown, we need to use this equation for calculating the coefficient of drag.
Is that 24?
That's 24.
Okay. And then the R is Reynolds number, right?
Reynolds number, yes.
Okay.
It's the same equation. It's actually written here.
Oh, okay.
So if Stokes' law, as written here, only can be used for spherical particles and laminar flow, we're going to always assume the particles are spherical. The problem is we don't necessarily know if the flow is laminar. So if the flow is laminar, and what Stokes' law uses is the simplified version. It uses this equation here for the coefficient of drag. If we don't know
Okay, so Stokes is for
spherical particles, laminar flow.
Okay.
Okay. So but the problem is if we don't know the coefficient of drag, then we're kind of stuck. And we'll go through a problem where we actually don't know the coefficient of drag. This will become extremely important in filtration when we look at filtration hydraulics, because filtration is entirely designed based on hydraulics. We won't consider chemistry at all in filtration. It'll all be fluids. So this same approach with the coefficient of drag and Reynolds number we'll use again when we talk about filtration.
Okay, thank you.
Okay. So we have the situation here. We have this rapid sand filter. We're looking at the time that it takes for this particle to settle. You're told that the density of water, you've looked up the density of water at 22 degrees is 997 kilograms per cubic meter. This density here is just because the specific gravity of the particle was originally stated as 2.65, and I just did the multiplication. So that's why it's what may seem like a strange number. And then we have this dynamic viscosity and the kinematic viscosity, both at 22 degrees C. So let's assume, the first thing we'll do is we'll assume a spherical particle and laminar flow, because we like Stokes' law. We like the easy route. So we have gravitational acceleration, density of the particle minus the density of water times the diameter of the particle squared divided by 18 mu. So V sub s is equal to 9.81 meters per second squared times 2644 kilograms per meter cubed minus density of water times the diameter of the particle, and we need that in meters. This was 0.1 millimeters, which is 1 times 10 to the minus 4 meters. And we will divide that by 18 times the viscosity, and that is 0.0094 meters per second. Let's check the Reynolds number. Make sure that it was appropriate to have used this form of Stokes' law. So Reynolds number is equal to the diameter of the particle times the terminal settling velocity divided by the kinematic viscosity. And that is equal to 1 times 10 to the minus 4, 1 times 10 to the minus 4 meters times 0.0094 meters per second divided by the kinematic viscosity, and that is equal to 0.98. It's less than 1, so it's reasonable to have used the form of Stokes' law that we did. If this was not true, then what you need to do is you would estimate the Reynolds number. So basically, it's an iterative process. You would first estimate the terminal settling velocity using Stokes' law. You then calculate R, and I didn't spell calculate R using the equation that I gave. You then calculate coefficient of drag, and then you calculate a new terminal settling velocity, and you continue to do that until it converges. So until the terminal settling velocity converges. So it becomes an iterative process. And we will actually have to do this when we move into filtration hydraulics. Time is equal to 1 meter divided by the terminal settling velocity, and that equals about 104 seconds or 1.8 minutes. So it takes roughly 2 minutes for that particle to settle. Any questions about this? As I mentioned, we will use this approach extensively in filtration. And this is just a plot of Reynolds number and the coefficient of drag and Reynolds number. And you can see here, if your Reynolds number is less than 1, it's where we can estimate the the coefficient of drag as 24 divided by R. And you can see how it deviates, and we need the more complicated equation if we're in that transition zone here, if we're in this transition zone. Okay. So moving into how do we actually use this in a water treatment process in the actual plant. We approximate sedimentation basins using this approach here, where we're assuming that there are 4 zones in the basin: an inlet zone, an outlet zone, a sludge zone, and a settling zone. Only in this settling zone do we have laminar flow, and do we assume that we truly have settling. We also will assume that the flow entering and leaving the settling zone is evenly distributed. So basically, as it comes in, a particle entering has an equal probability of being anywhere vertically in a cross-section of that basin. We'll assume that any particle that enters the sludge zone are captured, so we will assume that we don't have re-entrainment of particles in the sludge zone, and that any particle that enters the outlet zone is removed from the water. So I'm going to try and draw this, see how well I can do it with that on the tablet. But we have, think of this as our sedimentation basin. And we'll draw it as a rectangle. We have some portion of that basin that is our inlet zone. So this portion here is the inlet zone. So in that, the particles come in. So if we've got flow in here, what we're assuming is that if we have turbulent flow within, or transitional flow within this region, and any particle entering has an equal probability of being anywhere within this zone. We're assuming we don't have removal in that zone. We also have an outlet zone. That is this area here. So this is our outlet zone. We have flow out of the system here. Again, we'll assume that we don't have settling in that outlet zone. So we have, the flow is either transitional or turbulent, but we don't have settling there. And then the last, or the third zone we have is on the bottom of the tank, and that is our sludge zone. Particles settle, they hit the sludge zone, and they remain there. So we're assuming that no particles are re-entrained once they hit that sludge zone. So consequently, a particle enters here. That particle has the potential, okay? In this case, it's not removed. It doesn't hit the sludge zone, and it would actually, it enters the outlet zone and it ends up in the effluent. So that particle is going to end up here. On the other hand, we've got another particle. It enters here. It actually has the same terminal settling velocity. So notice the slope of both lines are the same. So the terminal settling velocity, both of these particles are the same. But the blue one is removed. So what we ultimately want to be able to do is to be able to predict what fraction of particles will be removed in the sedimentation basin.
Was the top one or bottom one removed?
So the top one, notice the top one hits the blue area here. So the top one ends up in the outlet zone, and it's going to end up here. The darker blue one hits the sludge zone, and it's removed. So the one that hits the sludge zone is removed. So let's draw a different.
Thank you.
Okay, let's do this color. Okay, so let's take this particle here. It is a different, actually, we'll give it the same settling velocity. So this green particle, it settles, is it removed or not?
No.
No, because it hits the sludge zone. On the other hand, if it entered here, it would be removed.
Yeah.
Okay, so this is just another schematic attempting to show the same thing. So you have flow entering here. You have your inlet zone here. Typically, you'll have perforated baffles, and this is to try and slow the flow, impede the flow, distribute the flow, so that, as I mentioned, a particle enters this settling zone, has an equal chance of being anywhere in the vertical profile. And then you have the outlet zone and the sludge zone. So when we look at rectangular basins, the particle removal is dependent on the overflow rate, and we'll talk about that in just a bit. And that is a function of the design of the basin. So we have both a settling velocity and an overflow rate. The settling velocity is a property of the particle. The overflow rate is a property of the basin. And we're comparing the overflow rates and the settling velocities in order to determine what fraction of these particles are removed. So the overflow rate is equal to your flow rate divided by the surface area. Q is just volume divided by the detention time times 1 over the surface area. Volume is equal to the height times the length times the width of your basin. Again, this is divided by the detention time. And your surface area is the length times the width. So it's the surface looking down. Length cancels, width cancels. So your overflow rate is actually a function of the height of the basin and the detention time in the basin. And the percentage of particles removed is equal to the terminal settling velocity divided by the overflow rate times 100% for a rectangular basin. So you can see it here. This is height. So we have an overflow rate. This is our overflow rate here. We have a particle that has a terminal settling velocity that's 1/2 of the overflow rate. And you can see that if it enters here, it escapes. If it enters anywhere in the lower half of the basin, it will be captured. So if it enters here, it's captured. If it enters here, it escapes. So this equation here becomes critical in designing the size of the sedimentation basins. And what you'll see is we actually will use factors to account for the fact that we have these other zones. So we'll actually design the volume essentially of the settling zone, and then we'll use a multiplier to account for those other regions. We also have upflow clarifiers. Now these operate a little differently. As I mentioned, these have your mixer in the upper portion of the inverted cone. This is where you have the flocculation. So we'll just draw it. Okay. As if we had the paddle wheels. We wouldn't have paddle wheels, but we have typically an impeller flocculator here. So we have flocculation here. And then the settling occurs out in the inverted cone here. Still, the overflow rate is equal to Q over A sub S. So that doesn't change. What does change is my particle is settling this way. My water is actually flowing in this direction here. So my overflow rate is in the opposite direction. And because you have this inverted cone, the overflow rate, remember, is Q over the surface area. So this is equal to Q over A sub S. Your surface area is actually increasing as the water flows, as you move upward in the basin. Okay. So V sub 0 actually decreases as you move upward. The surface area that we use in the design is the upper surface area. So it's looking at it here. So it's this surface area. Here is what we use in design. With a upflow basin, if V sub S is greater than V naught, then you get 100% removal. If V sub S is less than V naught, you get 0% removal. So with an upflow clarifier, it's either 0 or 100%. For those particles that have a terminal settling velocity less than the overflow rate, they will not be removed. They'll end up in the effluent. So those particles end up in the effluent. Those that have a settling velocity greater than the terminal settling velocity will end up in the sludge, and those will be removed. And that's basically what I have here. Okay, so I think I'll stop there rather than moving any further. And we'll start on Monday looking at a sedimentation basin, and we'll actually start with the designs of a sedimentation basin. I don't want to start that problem now. Any question about sedimentation?
Yeah, do we have homework due on?
You have homework due on Wednesday.
Oh, okay. Were they all moved to Wednesday or just a few?
Everything's moved to Wednesday. I moved it to Wednesday just to be consistent. We kind of talked about that a week or two ago. And people said that it was better to have it on Wednesday. then on Monday. So I moved everything to Wednesday. So
Oh, okay. I thought it was just a few assignments.
yeah, so everything shifted. Hopefully that's okay. So participation 5 is due still on Sunday night. Homework 4, which is softening, is due on Wednesday. And with that, tutorial 1 is also due, and that's a conceptual drawing of a flocculation basin.
Dr. Maston, could you go to the slide that had, it was for discrete settling, and it was for a transitional flow between, with a Reynolds number between 2 and 500?
So basically, this is just a much more complicated equation for Reynolds number. This should be G. I'll correct that in the notes. So this is gravitational acceleration. So it's still the density of the particle minus the density of the water. In this case, the diameter of the particle is to the 1.6 power. You've got the density of the water to the 0.4 power, the absolute viscosity to the 0.6, and then the entire equation to 1 over 1.4. So I apologize. This is gravitational acceleration.